Okay, we're going to talk a little bit on chemistry. Now, normally, as you know, I teach face-to-face in this class, so therefore, I won't be able to cover all the slides because we don't have the same degree of interactive nature. But so we will kind of loosely do these PowerPoints and get the concept across. Okay. First of all, chemistry is the scientific study of matter. Matter is anything that occupies space and has mass. Now, the term mass sometimes used to be used interchangeably with weight, but they are two different things. In order to have weight, you must have some pulling force like gravity. Mass is more of the quantity of particles. When you have the quantity of particles per some unit volume, that's the density. The more particles per unit volume, the more dense it is. So therefore, weight needs a pulling force. It could be gravity or it could be something else. All right. Matter is made up of something called elements. Elements are the building blocks, and we have certain elements on this earth. We can say that an element is a simple, pure chemical that cannot be broken down by ordinary chemical means. That means it's the simplest that you can get. You cannot break it down by ordinary chemical means, but you could change it by extraordinary, like a linear accelerator or something of that nature. You could change one element to another. We have 92 naturally occurring elements. 92 naturally occurring elements. But when we look at the periodic chart, which I encourage you to get one, print one out, go online, then you have certain, if you look here, you have 92 naturally occurring ones, but once you get past that, there are some others, and this is an older chart, that would be non-natural, synthetic. The only way to get a synthetic is to bombard an existing one and change it. But by doing that, you don't always get it on the chart, particularly if it disintegrates quickly and is not able to be measured to give the proper parameters. All right, so we go back again. We're saying there are 92 naturally occurring elements. On the periodic chart, you list one atom of the element. So in other words, on the periodic chart is listed the characteristics for one atom of an element that you have. All right, we go a little further. In the fields of chemistry, I'm going to separate them out into inorganic and organic. As a matter of fact, I have two PowerPoint presentations for you. One is on inorganic chemistry and the other one is on organic. We currently are in the inorganic. Any molecule that is an organic molecule must contain carbon, but it must contain it in an organified form, basically to also have some hydrogen. So as I allude to, CO2 contains carbon, but it's not organic because it's not a hydrogenated carbon. All right. We go further, and I'm going to say in this particular course, we're primarily interested in human chemistry. Okay. So human chemistry, being a life form, is based off of organic chemistry. Organic chemistry is life-based. Remember, we had two, inorganic and organic. Under organic chemistry, you can put different ones: biochemistry, polymer chemistry, like oil and glass, geological. Because what we're interested in is the chemistry of the existing now. Remember, oil is dead organisms that have been compressed in the earth. So our study is on biochemistry, which is subsumed under organic chemistry. Okay. We go further. Under our biochemistry, we're interested in animal because there is a plant biochemistry. When we go to animal, there are a bunch of different animals, as you know. Ours in this course is interested in human biochemistry. Now, there were 92 naturally occurring elements, but when we look at life itself, really we're only involving 26 elements. Now, we do have some others that pass through our body in our food and so forth like that, or inadvertently through our body, but our primary interest is on these 26 different elements that comprise the human body. All right? When we look at that, some elements are more prevalent than others. So 96% of elements are our carbon, hydrogen, oxygen, and nitrogen. I oftentimes call it CHON, C-H-O-N. That's the most abundant. The next most abundant group was our phosphorus, potassium, iodine, sulfur, magnesium. And then we have this less than 1% type, less than 0.01%, and that's our trace elements, which we have very little of. Many of these act, as we'll find in my organic PowerPoint, as what we will call cofactors in enzymatic reactions, but we're not ready for that yet. Okay. Here's a chart that you can look at in my PowerPoints again to kind of list these. You can see of all the elements, oxygen is the most abundant that we have in our body, followed by carbon. Okay? Remember I mentioned that each element is represented as one atom of that element. So what an atom is we'll define it as the smallest intact chemical unit. Now notice my word intact. It's not saying that we don't have anything smaller. We do, called subatomic particles. But as an intact entity, it's the smallest. So an atom is the smallest intact entity. As I alluded to on the periodic chart, each element is represented by one atom of this. That particular atom, I'm going to say, using my terms, is in its best form. Okay? The atoms are made up of something we call subatomic particles. The main subatomic particles we have are the neutrons, we'll speak on the protons, and the electrons. Scientists have even come with the subatomic particles that we have. But I won't really get into that. I'll just mention them, but that's beyond the scope of this particular course. When we look at the subatomic particles, I want you to glance at that we have neutrons, protons, and electrons. Neutrons are the largest by just a little bit. This is mass in grams. The charge on a neutron is a neutral charge. Protons are slightly smaller, and their charge is positive. Electrons are considerably smaller, about 1,280 times smaller, and they have a negative charge. An atom has what we call an atomic nucleus, and the atomic nucleus contains the neutrons and protons floating in a small space almost at the speed of light. The electrons travel around the nucleus like in a cloud, we'll say. So in other words, atomic nucleus, neutrons, protons, electrons traveling around. So in this particular illustration here, you can see here would be the atomic nucleus right here of carbon and hydrogen, and this would represent the electrons traveling around there. All right. I mentioned to you, which I'm not going to get into, is that there are subatomic particles. This is beyond the scope, but I just have in my PowerPoint to show you that these are some of the subtypes. Okay. We go further, because that's not the scope of this course, is how big is an atom? The usual atom is about, on average, about 10 to the minus third picometer. The average, and that would be the atomic nucleus, the middle portion. The width of the entire atom, which would include the electrons, is about 10 to the second picometer. Now, these are very small, but the difference between the nucleus and this would be 10 to the fifth. That is almost like placing a marble in the center of the old Astrodome and letting the roof be where the electrons would travel. So if you can imagine this, an atom has a lot of empty space. Here is to show you the metric system. You need to be somewhat familiar with the metric system because that's what science deals with. And so kind of glance through that if you would. An atom has certain descriptors about itself to describe the atom. Okay? The main descriptor is going to be something called the atomic number. The atomic number is the number of protons. If you change the atomic number, you actually change the element. So in other words, the synthetic elements changed the atomic number in order to get that. The atomic mass, in a rounded fashion, is to say the number of neutrons plus protons. Now that is in a rounded fashion, which you'll see in the text. On the periodic chart, though, they look at it in a different way. It is being looked at by something called the atomic mass units. The atomic mass units, which I will attempt to describe. The atomic mass units. Or, going by the person that came up with that, a Dalton. In science, we use eponyms. Eponyms in the old days were used just to name something credible after a person. We're kind of getting away from that. So Dalton would be the same thing as an atomic mass unit. John Dalton is the one that came up with this concept of atomic mass unit. And he wanted to make the description of the size of the atoms relative. So he picked carbon-12, and said that's going to be, should we say, his gold standard. And he came up with his definition that one atomic mass unit is 1/12 the mass of carbon-12. 1/12 the mass of carbon-12. Okay? So 1/12 the mass of carbon-12 is what he conceptualized as one atomic mass unit. If we go to carbon, please look at your periodic chart. It has an atomic number of 6, which means it has 6 protons. It has an atomic mass on the rounded fashion of 12, which means it has 6 protons and 6 neutrons using the rounded mass measurement. On the periodic chart, the number of electrons always equals the number of protons because the atom is in its purest form. Thus, that makes it neutral. 6 positives and 6 negatives. So, to calculate the total atomic mass of carbon-12, if I wanted to do that in grams, I would do this calculation. I would look back and say that each proton is 1.674 times 10 to the minus 24th, and there's 6 of them, plus 6 times the protons, 6 neutrons, then 6 times the protons, plus the electrons, and that would give the complete atomic mass of carbon. So the complete atomic mass of carbon would be 6 times the number of protons in neutrons, I keep saying neutrons in grams, plus 6 times the protons, plus 6 times the electrons. Then if I divide all of that by 12, because Dalton said 1/12 of the mass of the carbon-12, that would equal a 1.66 times 10 to the minus 24th as being the size of 1 AMU. Now, for those not astute in chemistry, don't get too heavy into this because I'm not going to be asking you that, but I will use it a little bit later. So don't get all bent out of shape because I'm sure many of you have not taken any chemistry. All right. Now I go to what I'm going to call deviations of the atom from the pure form. Deviations of the atom from the pure form. So now I'm going to talk about isotopes and I'm going to talk about ions. But I'm going to do that in the next video. Thank you very much.